All right, part 2, here we go. We're on number 7. Give an explicit formula for the sequence. Well, the nice thing about this is they tell you that it's arithmetic, so you know the formula explicitly is going to look something like this from your formula sheet. A sub 1, remember explicit is just the one-liner version where you use n as a big variable sort of. Not just a subscript, but you use n to calculate with to find out what is the nth term. So yeah, you need to know the ingredients for that. Is you need to know the first term. You need to leave n in there. There's going to be n in the end because n is what is going to be the variable that's used to calculate what's going on at the nth term. But then you need to know what the constant difference is. Since they tell you it's arithmetic, you know there's something constantly being added as we go term to term. You only need to see 2 of those really to figure out what that is. The constant difference here is what we need to do to get from 243 to 228. Is that minus 15? Yeah, okay, so a sub 1 is 243. What this is saying is the nth term is 243 plus n minus 1 copies of, I would do it this way, negative 15. Now you could leave it like that. That's perfectly fine. I'm going to change to optional color. You could also say something like, there's a bunch of different answers for this. Notice how they say and, because you could do it a bunch of different ways. Some people like to do this more, 243 minus 15 of these n minus 1s. Some people don't like n minus 1 parentheses. They like to distribute it. And then that would be something like, I'll be the ghost first term, be add 15 back here, it'd be 248, 258. This is the same thing, 258 minus 15n. That works too. Any one of these formulas, if you put in n, say I want to know what the 100th term is. I put in 100 for n, I calculate this whole thing, it'll tell me what the 100th thing actually is. Whereas recursive formulas can't do that. Recursive formulas depend on the previous number to tell you what the next number is. And so they come in 2 parts. There's always an a sub 1. Tell you what the first term is. I got to tell you what terms are in the sequence as we move along based on what the previous term is. And it's got that huge caveat in it. We're talking about for all n greater than or equal to 2, because this is the first one. And n is a natural number, and who cares? And I'm not going to make you do any of this stuff, but yeah, that kind of goes on there. So this is all part of the description of what a recursive formula has to have. It has to tell you what it is when the n is 1, like what the first term is, and when it's any one of these numbers for n also. This isn't about the value of a sub n being greater than 2. It's about the n being bigger than 2. It's talking about the second term and beyond. This is what this is saying. Second term and beyond is such and such. Okay, so the first term here is 243. And if I was going to type this into the calculator and make my calculator go boom, 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 when I hit enter, 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 I would have to say answer minus 15. Answer minus 15 when I'm talking about things that are bigger than 2, bigger than second term and beyond. Okay, so that's it. That was a long explanation, sorry. I hope you fast forwarded if that was too easy. Okay, number 8, almost exactly the same kind of process, but now we're talking about geometric ones. Give an explicit formula for this geometric sequence. Nice, they told you that. The formula for this in general on your formula sheet is it's g sub 1 times the constant ratio to the n minus 1 power, which here is, it's weird they're asking explicit before recursive. Usually you do that the other way around. All right, that first term is 5. Constant ratio here, that's probably the hardest thing to figure out. What are we multiplying by as we go from term to term here? Well, that can always be found simply by taking the second term and dividing it by the first term. 5 times what is 95? Well, you've been doing that since pre-algebra. It's like you use division to sort of figure that out. 95 divided by 5 is 19. So 19 is the constant ratio that I'm taking to the whatever term I'm on minus first power. So if I needed to find the 100th term in the sequence, I put 100 in for n, and bam, there it goes. All right, B, recursive. Again, it's going to look like this. G sub 1, what's the first domino, and how do I knock down the next domino? For all n greater than 2. Would I count off if you left this off a test? I can't imagine doing that. That would be cruel and unusual. Not that I don't do things that are cruel and unusual, but this one's really silly. Okay. G sub 1 is 5. G sub n is answer times 19. I take 19 times the previous number to get the next number each time. Answer times 19. You can say 19 g sub n minus 1. That's fine. Each term is the previous term times 19. All right. Whoa, that's really big. Okay, this does not mean, to recycle the previous joke, expand the expressions does not mean to make them bigger, wider like this. Expand the expressions means use Pascal's triangle, or, you know, foil this and wait and run out of time. I wouldn't do that. To figure out what 5x minus 2 looks like if it wasn't all nicely factored like this as a cube. So actually multiply 5x minus 2 times 5x minus 2 times 5x minus 2, but we have a shortcut for that. And I'm going to explain this in a slightly different order than I have been because I think people are confused about what's going on in the exponents in the middle of this thing. The first term is going to be some number of 5x's cubed. The next term is going to be some combination of these things being multiplied up. Now the combination will look like this. I take the 5x's and I square them times the 2's. The next one, slightly different, I ratchet down these exponents. It's going to be 5x, and now I'm going to square the 2's. And the last one is just the 2's by themselves cubed. So that's how the exponent thing works, and I think that people were confused about that because I always did this part last and it was in the middle of all that other junk and it was harder to see. But you see the exponents on these things. First of all, it's 3 and 0 in this one. And here it's 2 on this one and 1 on this one. And then I go again and go one more step in that pattern. 1 on this one and 2 on this one. The last one is 0 and 3. So it's kind of like we were saying, like if you had to list possibilities for rolling dice, this is all the ways to have a sum of 3. 3, 0, 2, 1, 1, 2, and 0, 3. And I didn't even write the ones that had 0. Like I'm not going to write that this is times 2 to the 0th power. And I don't put a little 1 here because I don't need to do that. But that's what's going on. 3, 0, 2, 1, 1, 2, 0, 3. Now, the part that I was so excited and I always started with all these times was the Pascal triangle part. The Pascal triangle part is the coefficients that go before these. This would be the third row of Pascal's triangle, which is, oh, let me write it up here. I actually do have plenty of room. Here's the first, I think for number 10, I'm going to need one more row. Do I have more space? The fourth row right down here is going to go 1, 4, 6, 4, 1. I need that for number 10. Okay. And by the way, you'll have that on the test too. So the row I need here for number 9 is this fourth row, 1, 3, 3, 1. So 1, not going to write it. 3, 3, 1, not going to write it. Now, I'm happy with you leaving this like this. The book would probably want you to keep going and say what 5x cubed is. That's actually 125x cubed. What is 3 times 5 squared times 2x squared? That's 3 times 2 is 6 times 25 is 150. I mean, this does look a little more professional. 3 times 5, no, these will just be x's. 3 times 5 times 4 is 60, and 2 cubed is 8. So lo and behold, if you were to multiply that out by itself 3 times and foil it again, you'd get that. Isn't that a nice shortcut? Okay, 3x plus 2y to the fourth. Again, I want to do the same thing. 3x to the fourth at this end. At this end, we're going to have all the y's, 2y to the fourth and no x's. And in between, we're going to have those different sort of cross-fade exponents for this thing and this thing when they get multiplied. So the next one is going to be 3x cubed 2y. Then I'll borrow one more from this one and get it over here. 3x squared 2y squared. And the other one, the last one in the middle here, I didn't give myself quite enough room. 3x to the 1 2y cubed. Well, this coordinate's, or sorry, this coefficient's gonna be 1. This coefficient's gonna be 1, so I don't need any room there. The coefficients in between here go 1, 4, 6, 4, 1, because that's what that tells me. So 1 of those, 4 of those, 6 of those, 4 of those. Okay, now again, that's perfectly fine. You can leave it like that. The book would want me to go one more step. Bam! So I went ahead and did it. There it is. All these little terms simplified. I don't know that you need to have that. I mean, I'm not gonna count off if you don't do this last step. It's weird that these two both turned out to be 216. That's kind of a coincidence. I think it's because the Pascal's triangle thing here with the 4 and the 6 are kind of the opposite of the sort of the common denominator sort of deal over here with the 3 and the 2. The 4 and the 3 and the 2 and the 6 happen to produce the same. Anyway, that was just an interesting fact. That doesn't always happen. All right, so yeah, 3x plus 2y to the fourth power is all of this. All right, 20th row of Pascal's triangle. That looks like this. 20C0, 20C1. if you missed this, 20C2 dot dot dot, and the end would be 20C20. And remember, it's symmetrical and all that nice stuff. Think about how there would be 20, that's a 9, by the way, it looks like a 4. There would be 21 entries in this row because it starts at 0, goes to 20. The beginning and ending is always 1. The ones right inside that would be 20 and 20. Then that's when they start to get interesting after that. But anyway, it's symmetrical. There's maybe a middle number here, and then it's completely the same forwards and backwards. So the beginning of the line looks like the end of the line, all that kind of stuff. That always happens. What are the first four entries? Oh, I got to actually figure this out. The next one would be 20C3. And this comes out of the calculator. 20C2 and 20C3. 20 math, probability, NCR2. And I'll just do this. 20 NCR3, 190 and 1140. I'm kind of a little bit off here, but that's vertically not aligned. Anyway, that's what those are. And then coming back from the end is going to be the same thing. 20C18 is 190. 20C17 is going to be 1140. And of course, there's a bunch more entries in between. But that's what that's going to look like. So here's your answer for A. And here's your answer for B. All right. Oh, by the way, I'm on Pascal's triangle. If I were to add up the entire row, do you remember what that adds up to? Sum of, that's an M, of row 20. In case you ever had to know this. Oh, it's probably the next problem. I haven't even looked at it yet. It's 2 to the 20th power, by the way. Isn't that cool? Okay, file that away. All right, I went ahead and typed these in for number 12. This would be the middle of some row, and remember, it's supposed to be symmetrical. So yeah, of course, it's going to like start repeating and go backwards. This would be the actual middle. The rows below you can find by adding up the rows above. So whatever number goes here is going to be the sum of those two. I'm making big circles because they're huge numbers. Didn't leave myself much room for the biggest one, and some like that. So I would just add these things up and find that out, and those are large numbers. On my calculator, I find out that the first one, you know what? Let me get rid of these circles. They're kind of crazy. I didn't get rid of the brackets, but anyway. If I add that one plus that one, I get 9, 6, 5, 7, 700, which is going to be the same as this. I mean, after all, they're the same numbers. 9, 6, 5, 7, 700 numbers. And the middle number is add those two up. Which is, can I leave myself some more room? Which is 10, 400, 600. So there's your, comma separated for millions. There's your huge numbers for whatever row that is. Okay. Okay, what's nice about this one is they tell you it's geometric. They're asking, okay, does it converge or not? The whole test of whether or not it converges has to do with R. If R is between 1 and -1. In other words, if it's a exponential kind of shrinkage number between 1 and 0 or negative, then it's gonna converge. If not, then it doesn't at all. So what am I multiplying by here to get down this list? Well, I could take -10 divided by 8 and figure out what that is. Well, I don't even have to do that. -10 divided by 8, I can tell, is outside of that range. Its absolute value is greater than 1, so divergent. Thank you for playing. Game over. All right, so I'm on to number 14, and I have about a minute left. There must be some multiplier here that's less than 1, otherwise this would be a silly question. And I would just take 12379.2 divided by 15474, and I find out that that ratio is times 0.8. So yes, that is convergent. We're talking about a series here, so I don't actually want to know what the infinite term, like what is it turned into. I know that's going to be 0. I'm actually trying to find the sum at infinity, which is the nice formula, just g sub 1 over 1 minus r. G sub 1 I have, and 1 minus r, I can usually do in my head, 1 minus 0.8, it's 0.2. I'm decreasing by 0.8 every year, it's like I'm retaining 0.2. And I divide that, and I get 77,370. All right, that's the end of part 2. I'll see you in part 3.